Hello, and today we'll be evaluating the bounds of iterated integrals. We're going to be looking at an example exercise. So here we have the double integral of the function xy squared, where where R is the finite region in the first quadrant, bounded by the curves y equals x squared and x equals y squared. So, the first thing you have to do is, well, first of all, this double integral itself is quite easy. But what's a bit confusing is what are the bounds for these integrals, right? So first, in a double integral, you have two parts, one with respect to y and one with respect to x. So the one with respect to x is you'll be looking at the horizontal lines, right? You'll be just making horizontal lines of the area. So the dx is the horizontal bounds and dy is the vertical bounds. So you would have to either draw, or I mean, if you're very like mathematically creative, you can also see it in your head. But I like to draw it. I'm not gonna draw it right now. I'm just gonna show it in Desmos. So here we are in Desmos. We can see both of these curves mapped on Desmos. So the one is y equals x squared, and the other one is y equals the square root of x. Right, as we could see, we actually had y equals x squared and x equals y squared, but I have rewritten that as y equals the square root of x, so it's both in terms of y, right? So, horizontally speaking, right, so dx, we can easily see that the intersections are 0, 0, and 1, 1. And you don't have to draw that to see that, you can just mathematically calculate it, because you have this, right? You can obviously see that for y is 0, x should also be 0, because 0 squared is 0. And for y is 1, x squared is also 1. So your horizontal intersections would be, just your intersections in general, they would be 0, 0, and 1, 1. So horizontally speaking, that is going to be, so the lower bound would be 0, and the upper bound would be 1. Okay, so, so we found the bounds for dx. Now we need to find the bounds for dy. And for dy, we would be drawing vertical stripes. So going back to Desmos, we can see that the black curve is above the red curve. So this would be the upper bound, and this would be the lower bound. So the upper bound is the square root of x, and the lower bound is x squared. Because, as you can see, if you were to draw like vertical lines to calculate this area, then you would go and you would take the y value of the square root of x, you would subtract that with the y value of the red function, which is y equals x squared. So your upper bound is the function that is like the highest. So in this case, this is the square root of x, and your lower bound is x squared. Okay, so we found the upper and lower bound for dy, and now all we have to do is calculate the double integral. So, rewriting that, we would get the lower and upper bound for dx, and the upper and lower bound for dy of the function xy squared. And then you need to be careful. It's going to be dy dx and y, because when solving double integrals, you work from the inside to the outside, right? And we know that these bounds are for dy. So like this. Cool, so let's solve this integral first, and then the rest will be very easy. So solving this is not going to be very hard. We just integrate with respect to y, meaning that x is a constant, and we treat x as a constant. So the y is going to get another power, and 1 divided by the new power. right? But we mustn't forget the x, like so. And then the upper bound is the square root of x, and the lower bound is x squared. And don't forget that we are integrating with respect to y, so we fill these bounds into the y and not into the x, like so. So when filling it in, we get 1/3 x, and then first the upper bound, which is the square root of x to the third power, which is just x to the half power to the third power, and that's going to be x to the power of 1.5. Oh, you have another x there, so that's going to be x to the power of 2.5 minus, and then the lower bound, so 1/3 x, and then we fill in into the y, we fill in x squared, right? So we get times, and then y, which becomes x squared to the power of 3. So that's going to be x times x to the power of 6, which is just x to the power of 7. So we just have this little equation here, right? And you might think that you need to somehow like simplify it more, but the only thing you can do here is just factorize out the 1/3, sorry, to get this, because we are not done with the exercise yet. We still need to do the outside integral, which is this, and then with respect to x. So we can see here, we just have to fill in this integral and solve it again, right? Because this is the form. We solved this, which became this, and then we need to solve the outside integral, right? But we see that 1/3 is a constant, so we can move it out of the integral. There's just a rule. And then write this here, dx. So we need to find this integral. So 1 divided by 3 to the power of 4. Let's rewrite this as 7 divided by 2. So 1 divided by 7 divided by 2 is just 2/7. Cool. And now we have minus 1/8 of x8, right? Because we have x to the power of 7. The integral of that becomes x and then plus 1 to the power of 1, right? Because n plus 1. And then 1 divided by n plus 1. So 1 divided by the new power. So that's just going to become 1/8 times x to the power of 8. And our bounds is 1 and 0. Cool. So filling that in is just 2/7 minus 1/8. And yeah, 0, here's gonna be 0, here's gonna be 0. So that's all fine. So here you just can multiply this by 7, multiply this by 8, and get 1656 minus 756, which is 956, which is equal to, let's see if we can make it any easier. No, we can't. Let's see, are we done here? No, because we had the 1/3 outside of the integral. So this times 1/3 is just 356, right? Because this is essentially, this becomes 3 times as small, right? So you can either make this 3 times as big or 3 times as small. Cool, so this is our answer. Moving on to the second problem. Hold on, let me remove this first. Okay. So here we have the double integral of x cosine y, where D is the finite region in the first quadrant bounded by the coordinate axes and curve y equals 1 minus x squared. So let me map this onto Desmos and I'll be back. So this is our function, y equals 1 minus x squared. So here again, we're just looking at the horizontal intersections and the vertical intersections. So we don't even, in the first quadrant. So this can be easily calculated, the horizontal ones. We just need to see where does this function cross the x-axis, right? So the function crosses the x-axis when y equals 0. So filling that in, we get 1 minus x squared equals 0, or x squared equals 1. So x is 1 or x is minus 1. But x is minus 1 is not in the first quadrant, so this is our only option. So x equals 1 would be our lower or upper bound? Our upper bound, because this is the right side, right? And we're looking at this first quadrant. And the right side, we always go from left to right, right? So this is our upper quadrant for dx. Sorry, our upper bound for dx. And obviously our lower bound would be 0, because if you go back to the question, it says the region is bounded by the coordinate axes and the curve. So let's just write it down. Cool. And now when we look at the vertical stripes, so the vertical bounds for dy, we can obviously see that if you want this area in the first quadrant, what we need to do when we look at it with respect to y, we just take infinitesimally an infinite amount of vertical stripes. And when we take a certain vertical stripe and we want to calculate its area, we just take the y value of this upper point and subtract it with the y value of this lower point. And since this region is bounded by the x and the y-axis, we keep taking all of these y points of this graph and subtracting them by what? By this x-axis here, right? But the x-axis is always 0, y equals 0, right? So our lower bound is y equals 0, and our upper bound is just this graph, right? Because we go from down, we go from the bottom all the way up. So our boundaries are for dy is 0 to 1 minus x squared. Perfect. So we've done the I wouldn't say it's complicated, but it just takes a little time to understand what you have to do. So now we just solve the integral. We can choose whichever one we want to solve first, but let's write it down. Yeah, I think I'm going to solve this one first, it seems like. X cosine y, and then dy dx, right? Because this one is dy, the inner one. And then we're going to solve the outer one. So solving this integral, 1 minus x squared 0 x cosine y dy. So we do is we integrate with respect to y and we treat x as a constant. So you can do this just like biologically thinking about it, or you can say like, okay, so if x is a constant, let's just visualize x as if it were a 3 or something. So how would you be able to solve this? So we know that the integral of cosine is sine, right? So in this case, if you were to solve the integral, the 3 would stay, right? So the integral of this is just simply x sine y. And we integrate with respect to y, so we fill the bounds into the y. So y is equal 1 minus x squared and y is equal to 0. So when you fill this in, you simply get x times sine 1 minus
So
x
this
squared.
part can be easily solved using u substitution. So what you have to do is you need to rewrite this inner part of the sine function as, so let's say that u is 1 minus x squared. So then du equals 1 minus x squared dx. Rewriting that would get dx equals du divided by 1 minus x squared. Sorry, what am I doing? I forgot that we need to differentiate it. 1 second. So du equals minus 2x dx. So dx equals du divided by 1 minus 2x. So when rewriting this integral, we get the following, which is this, and then the inner part of the sine function is u. So this is du divided by minus 2x. So let's put this divided by minus 2x with the x, and we can clearly see that the x will get crossed out. So we would have minus 1/2 here, like so. And now it's just we just solve this this integral, and so we can move the minus 1/2 outside of the integral because it's constant. So sine is the integrate is minus cosine of u, and then the upper and lower bounds are 1 and 0, so equals minus cosine 1, and then minus cosine 0, and then all of that times minus, and we know that cosine 0 is 1 and cosine 1, it's going to be a difficult radian, so let's just keep it that way. Anyways, so minus 1/2 times minus cosine 1, and cosine 0 is 1, so minus 1 is just plus 1. Now let's factorize this. Let's put the minus inside, getting this cosine 1 minus 1. So thank you for watching, and this is our answer for this exercise.